Okay, so last for the day, but not least, I would say. So at some point during all this, I thought, okay, we conclude the day with the project, with the results of the project, and then I was like, yeah, but I know there's some cool stuff happening, right? So we should at least give a glimpse of what's going on and what's going to be the legacy of this project, and basically how some of the results will be exploited into future research. And then Blake came to mind because he's the one who is tasked to answer all the questions because we couldn't do it. So no pressure, Blake. And we are all half drunk, so it's fine.
Thanks, Alessio. It's a real pleasure to be here and to get to talk about some of the work that we've been doing really since even a little before WARMCOASTS. Alessio asked me to start to give a talk, WARMCOASTS to HISEAS, which is the name of a project that recently was funded that I'm a part of. And kind of pitched it to talk about what's next, but really is what's going on now. The fun never stops. There's no break between WARMCOASTS and what's happening next. There are a lot of people that have been a big part of different aspects of this project. Many of you are in the room. I'm not going to go through all of the ways you've contributed, but I am very appreciative, and it's been really fun to work with all of you. I realize we have a hard time to get out of here, so you might see me skipping some slides. Alessio told me to aim for about 6, and 6:10 I think we're out of this room, right? So, okay, so I'll try not to push it too much. So I always like to start, or I really like to start with this record of CO2 over the last 800,000 years, CO2 reconstructed in the atmosphere from ice cores. And when it gets to the end here, you'll see the Mauna Loa record, the instrumental record. And I really like this data set because we can see a few things. We can see climate change broadly. We have warm interglacials and cold glacial periods. And we can see, most importantly to me, that things today are very different than they have been in the past, right? And I think this really, it speaks to me because I think as earth scientists, we have a real responsibility here to try and understand what this part of this curve means for our future. And of course, one thing it means is that the planet is warming. We've looked at a few different observational data sets of temperature. This is surface temperature anomalies in 2003 compared back to a few decades prior. 2023. In 2023 was a pretty warm year, and importantly, the places that the planet is warming are not uniform, right? The poles are warming quite quickly. They have really dark red colors towards the poles. And that means that the ice sheets that still remain probably are going to be responding to that heat, right? And when it comes to thinking about the ways that climate change are going to affect all of us, right? Affect infrastructure, affect people, our lives. Heat strokes is one, but I think sea level change, and especially the sea level change caused by the melting of ice sheets, right? The large ice sheets where all this volume is. This is really the scary aspect of what's coming that I think we really want to try and understand as best we can. And it's a hard problem, modeling how an ice sheet is going to respond to some hypothetical climate, a coupled climate ice model. This is a hard task. There are a lot of really smart people working on it. As a geologist who looks to the past, who likes to go and look at ancient records of what the Earth looked like in the past, we also have a way to contribute to this story. And this talk is mostly about what Andrea set me up nicely for earlier, trying to fingerprint the sources of excess melt in the last interglacial period. And the story, for me, really starts with this COP 2009 paper. I did my PhD 2010 to 2015, and in the same actual room that Bob probably wrote this paper. He was gone by the time I was there. But I didn't study sea level during my PhD, and for my postdoc, I kind of came from deep time into this recent sea level community. and the link for me was carbonate sediments. And this paper really spoke to me, and I think it speaks to a lot of us. It's almost sacred at this point. The level of sophistication and the sort of things Bob did in this paper with varying a lot of different GIA models and ice configurations, he really did a first pass at what I'm trying to show you today. So in this paper, they looked at sea level indicators from 42 different locations, and they used them to sort of invert back for what we usually cite as this 6 to 9 meters of sea level change, 6 to 9 meters of peak sea level during the last interglacial, and this is the sort of iconic figure from this paper. But part of this inversion was also trying to back out what the ice sheets were doing. His posterior and priors were pretty much the same for the ice sheets, so at that point, the approach and or the data wasn't quite resolved enough to tell us very much about where the excess melt was coming from. During my postdoc, Alessio and a few others brought up this 2021 paper, which summarizes a lot of the work I did in my postdoc. We had this idea that we really wanted to just, let's go to one region on this map where we think we can get really precise chronologies and really precise sea level indicators, and try and constrain the GIA component of that sea level calculation, paleo sea level calculation, a little bit better. And then maybe we'll go and expand towards the global record. And so I'm going to kind of tell you that story today. This is a figure, it came up earlier from that paper, and in that work over quite a few months, several different field seasons in the Bahamas and Turks and Caicos, we put together this database that basically showed peak sea level across this archipelago, varied quite a bit during the last interglacial. So in the northern part of the Bahamas, on New Providence Island and Eleuthera, you can find very precise sea level indicators, about 7 meters, 6 to 7 meters above mean sea level today. And if you go down to Great Inagua, where there's this amazing coral data set from Bill Thompson, there's these great coral reefs and there's lots of marine sediments, but nowhere on the island can you find them above about 2.5 meters. So this gradient and relative sea level, this was what we were trying to create so that we could constrain the uncertainty we have in the GIA calculation that goes into trying to back out what global mean sea level was. And I say global mean sea level, and I want to mention something that really resonated with me earlier in Andrea's talk, that we spend a lot of time and have spent as a community talking about global mean sea level. But what we really care about is the individual ice sheets. And part of the reason we do it is that it's easier than solving the individual ice sheets, and it's also intuitive. If I tell you there was 1 meter of excess eustatic sea level globally, you can imagine that as some volume of ice. And you don't have to prescribe it to a place. And in this talk, I'm going to kind of take us away from that framework and into a framework of thinking about the individual ice sheets. So in this paper and in a lot of papers that have tried to say, I have some observations of relative sea level in the past, I have some GIA models, I'm going to run a GIA model with no excess melt during the last interglacial, and whatever the misfit is between that GIA model and my sea level observation, there must have been some excess melt, or if the misfit's the other direction, then there's more ice around. As we get later in the talk, we're going to look at some results that come from a lot of different GIA models, and I just wanted to point this out here while I have this figure. In the models we look at later, this flat line, which is the global modeled mean sea level, there will be excess melt during the last interglacial. So we're actually simulating a bunch of different possible excess melt scenarios. But in this paper, we said, okay, we have these observations that can constrain the rheology, and we started to build some of the statistical tools I'll show you later today. And we did this sort of inversion that backed out both what is the set of ice configurations and rheology that best fit the observations. And the main result, I think, from this paper was that the data in the Bahamas could be explained with a lower than 6 to 9 meter sea level excess melt. And secondly, the Laurentide ice sheet that best fit this data, so the Laurentide ice sheet at the penultimate glacial maximum, so stage 6, it either had to be smaller than the last glacial maximum, or it had to start melting sooner. Essentially, the impact of it on the GIA model, it needed to be essentially less impactful on this region, not very far away, a few thousand kilometers to the south. And that brings us to 2019, I think, was when WARMCOASTS started, and product one was Wallace. So around the time that paper was coming out, even when we started talking about the results, and probably even in some of the reviews, everyone's question was, well, why don't you just apply it to more data? There were a lot of challenges to solve to try and do that. I think we've solved most of them. I won't go into that too much today, but the obvious next step after that paper was how do we start expanding to more of this global information? And the Barnett paper, which came up a few times today, we kind of did the same approach in the southern UK, and then we used the differences in the sort of conclusions, this figure here, the conclusions from those two papers to say, well, this difference must be some kind of fingerprint, right? It's telling us about the actual gravitational field associated with excess melt. But in that exercise, we realized that this approach where we're not actually simulating excess melt during the interglacial was really going to hinder us. So we kind of had to go to this next step where we not only get the fingerprint, but we get the GIA, the ongoing isostatic adjustment within the interglacial into our models. So I'm going to eventually get to how we solve this and show you some results on a global data set. But I thought I'd spend some time just showing you what some of the data that we collected in the Bahamas looks like. And then we're going to look at the posterior inferences on that data in the final inversion later. So we're going to take a little tour to the Bahamas. And I'm going to break up the next part of the talk into sort of 3 parts. The first one I'll call sand, and we're going to look at the formation and deposition of sediments near tropical islands in the Bahamas. Part 2, we're going to spend a bit more time thinking about how sea level gets recorded in the stratigraphy of those sediments, so the ancient rock record. And then part 3, where maybe I'll end up rushing a bit and not show you as much statistics because it's 6 p.m. At that point, we'll just look at the results. So this is a photo in the background, a satellite photo of San Salvador Island. This is the southeast corner. And I think this is a really nice place just to look at on the map because you can see a lot of different environments in the modern that can tell us that we can sort of study and think about how modern sediments in this location record sea level. We're going to sort of zoom down onto the surface of San Salvador, and I'm going to show you some pictures and go on a transect here from the barrier reef towards the beach. So out near the edge of the platform, there in the Bahamas and in a lot of the Lakayan archipelago islands, there's a large barrier reef. It builds almost all the way up to sea level. You can see it in this photo sort of serving as a breaker. Those waves are probably breaking over palmata that are sticking out at the sort of the low swells of the waves. And they grow there mostly because the salinity and the temperature of the water there doesn't change very much. As you get into the lagoon, you start losing light because there's sand and it gets hot, and the corals don't like that. So there's a really productive region. It's hard to snorkel there and get good pictures because there tend to be pretty intense currents. But you can get some sense from this picture with Roger snorkeling over a palmata and this sort of high energy channel full of sand that you have these large frameworks of corals. And a lot of sand is generated here, and the sand's really important to our story, especially when we get into the stratigraphy part. So the sand is abrading off of the coral from storms and from parrotfish. As you work your way into the lagoon, sometimes corals find a place to survive, and they form these beautiful little patch reefs. And just like the corals out on that barrier, right? These are organisms growing underwater, but there could be a wide range of water depths at this patch reef. Here, maybe it's 1 meter, 2 meters of water depth, but I could swim around and find another one that looks just like this at 5 meters in the same lagoon. So when it comes to trying to reconstruct sea level, corals are great because they can tell us about time, but they're not the best most of the time, you know, with the exception of kind of what Andrea showed you earlier. Settings like this, it's really hard to put a precise sea level number on a fossil version of this. Sometimes you'll see that the tops of these patch reefs are covered in sort of red coral and algae, and we see this in the fossil record too. It sticks out at low tide at parts of the year, it doesn't die. That's a shallow water feature, maybe more precise than just the corals on their own. So we start thinking about the modern record in ways that we might be able to make observations like this and apply that to understand the past. But in the patch reef area, often there's not a lot of sand, so they tend to sit around hard grounds. So there's just these surfaces. They're not accumulating sediment. They're getting colonized by green algae, a big producer of aragonite in this environment. So these are Halimata and Penicillus. And if we keep going towards the island, we get to the beach. Everybody knows what a beach is. This is where you sit when you go on vacation. As a sedimentologist, I think of this as the place where accommodation space is filling. This is where the sand is going. Some beaches erode, so accommodation space isn't always filling. So you can see the beach here. There's just a little bit of sediment, but those waves, they are imparting information into that sand that we can use to sort of reconstruct the past. So they're sorting the grains, and they're leaving features like these air bubbles, essentially, that form as a wave crashes and pushes air down into the sand that get preserved in the fossil record. So when we see something like this is a photo in the modern, and I think you can see, well, you can't see the laser. You can see the laser now. You can really see these nice vertical escape structures associated with these air bubbles. So this is a sea level indicator of the top of a wave. Probably the highest wave that came on this beach in some time, so somewhere around high tide. But it's very precise. It doesn't happen in other places. And these observations will come back later in the stratigraphic part of this story. Above the beach, you often find a surface. We call this the ordinary berm or a berm. And this is a place where sand, often on a storm, might get pushed. But then most of the time, wind is just whipping that sand up and down the beach. It's not usually a place where a lot of sand accumulates. And in the rock record, that means it shows up as a surface. And that surface sort of separates those beach sediments from the dunes, the foredunes that sit above the surface. Here you can see these wind ripples sort of moving along this berm. That might be on Exuma. More wind ripples. So that transect had a bunch of different features that tell us something about sea level. And now we're going to kind of transition into part 2, thinking about how the stratigraphic record sort of can be harnessed to reconstruct a sea level story from the past. But when I think about this part, I want to, there's sort of 2 things that matter. In a place like the Bahamas, we really have to think horizontally. This is an accommodation-limited environment. It's not a layer cake like the Grand Canyon. So you don't get sediments that just pile up vertically. You get things that fill in whatever gap they can find, right? And so when you're doing field work and you're working on these islands that are remnants of past environments like this, you might go one ridge over and be in a totally different fossil environment. And 2, we have to be able to put time on things. So the corals that get fossilized, This is our main tool for being able to reconstruct or provide constraints on the age of the sediments we're looking at. And I'll show some dates later. All the corals that we've collected in the Bahamas have been dated at Lamont by Oana Dumitru, who's at University of Florida now. Turns out finding corals isn't that hard. One of the places that we've had a lot of success finding corals in the Bahamas is actually associated with these sort of big ridges that have drawn sort of right up against the reef wall. So this is actually meant to depict a Holocene dune. So when sea level came up in the early Holocene, these large foredunes formed. And in many places, they've eroded away. So there's not much of the dune left, just this little remnant. There's a new dune forming back on the other side of the lagoon. And this dune has sort of fossilized in place. And along its flanks, these dune foresets actually can be found dipping into the water. And these are great places for corals to grow. So here, where this dune has sort of been cut in half, there's not the sand that's kind of trapped back here in the lagoon doesn't cover up this rocky substrate, and when you jump in the water and snorkel here, you'll find a lot of corals. And here's a good example of these sort of encrusting forms of a pseudodiploria, which we find a lot actually in the last interglacial analogs of this environment. So a lot of the dates we've been able to put together come from dating corals like this. That one. And the corals themselves, maybe I want to go back just for a second. The corals themselves are not really as precise as we want, but when we want to think about the stratigraphy, we want to think about these places where the sand is accumulating. So when I go to try to search into the last interglacial record of these islands, if I can find places where sand and a beach has actually prograded over or buried corals, then I might be able to find the superposition of those fenestra over a coral, and I'll show you some records like that in a bit. That's sort of our holy grail. To do that, I will take you to Long Key. So this is a key on the southwest part of the Crooked Acklands platform. And this is a satellite image, but if I switch it over to a digital elevation model, you can see these sort of high elevation ridges. These, we think, are probably Aeolian dunes. And there's a slightly lower elevation plain here. It's a few meters above sea level, maybe 3 or 4. And it has these ridges. And so before we even came out here in the field, we spent a lot of time looking at maps and making some sort of hypothesis about what we'll find. And one of the patterns that emerged working in the Bahamas was that when we could find these prograding strands that intersected the edge of the platform, there was a pretty good chance we would find that sand sitting on top of the last interglacial barrier reef. So we're going to start sort of down here. The boat drops us off, and we're going to look at 2 sections, sort of walking our way north. The first one is kind of at this nose, and the second one is here. You can see Jackie Osterman and Billy DeAndrea taking some notes here along this cliff. And they're standing on a surface that's pretty flat, and it's sitting underneath these very large bed forms that are part of a foredune. This is a typical sequence we see in sort of the marine parts of the last interglacial record in the Bahamas, where you have a deep environment that shallows upwards, eventually to dunes. So we call this a shallowing upwards pair sequence. And what it really represents is that sand filled up this place. So there's a little snapshot of sea level somewhere around that beach. And in this location, not the fenestra. Go to further down, another maybe kilometer down the coast, I'm going to sort of walk you through an outcrop that is sort of the holy grail, or one of several holy grails we found here in the Bahamas. So down low, I'm kind of near the water here from this perspective. We have these cross beds full of shrimp burrows, a marine environment, very diagnostic. And as you work your way up through the outcrop, there's a noticeable change in how the crossbedding works. So up to about this surface, we have these trough crossbeds, and that goes up to about 3 meters. If I rotate the camera around to look down the coast now, keep your eye on the sediments above. They have a very different characteristic to the way the beds accumulate. So they're these sort of tabular, pinching out bed forms that dip down towards the ocean. And as we keep going, eventually you're going to find those units sort of lapping up on top of a fossil coral reef. And I'll highlight here the top of this reef sort of working its way. I think it's about 1.5 kilometers long here in this outcrop. And these sands sit conformably on top, and you get large corals that are sort of completely surrounded by sand in places. And I want to generate some really good dates from this reef. I'll highlight one here in a minute. It's about 119,000 years, so pretty late during the last interglacial. A palmata sample here. And I really love this perspective because you can see now that we've come to the front side of these sort of bed forms that were dipping towards the ocean, you can see they're quite flat the way a beach would be. So these are probably beach sediments. Here's Roger sampling that coral for Juana. And if we keep going up to the top of this beach, right up here, there's actually really nice fenestra and beach streaks that really kind of confirm this idea that we have both corals and a really precise sea level indicator all in one sort of story. Here's a fossil version of what we were looking at before. You can even see that same nice vertical escape structures somehow getting preserved. I really marvel at this. That's a 100-something thousand year old beach, and it looks almost like the photo I showed you earlier. So this outcrop's going to come back later. I'm going to show you what we do with data like this. But importantly, we know sea level pretty well from this observation. We know time pretty well with this one. And with superposition, we can use the coral to constrain some of the timing on the precise sea level indicator. Okay, so explaining variations in sea level. This is really when we get into the ice part of the story. And I want to start first with just a definition of sea level. And if you think like a sedimentologist, sea level is the ocean in front of you while you're sitting on the beach. It's a pretty simple idea. We're at a GIA and last interglacial workshop. We know sea level is anything but simple. It's related to the motion of the Earth, and it's related to this gravitational potential field, essentially some surface on the planet where the force of gravity is about the same. And because of that, especially that last fact, we can use variations in sea level in different places to actually back out things that might have caused Earth's gravitational field to change or land motion to change. And those things are our ice sheets. Here's an example of just a GIA model run. Cursor. And while it plays, I'm just highlighting how relative sea level in Long Key varies with respect to Hawaii. So places, I'll play it again one more time. Places that are going from sort of bluish to red are subsiding and sea level is going up. And places that are going from red to blue are uplifting, or sea level is getting sucked away, but sea level is falling there. These differences, if I ran a different model, I showed you a different model, those differences would be different, right? And so that is information about the things that go into the model, the fingerprints of the ice melt. This is just a picture sort of depicting, well, what would ice melt look like? What would sea level change look like if you instantly melted part of the Greenland ice sheet? And you get different sea level signals depending where you go. So we're going to leverage that here in some of the work that I'm about to show. Leverage that fact of nature to try and learn something about the past. So, okay, we want to explain variations in sea level, and I'm going to try and demystify some of the statistics and math that we use. It's really relatively straightforward. There's not a lot of complicated. The GIA models are more complicated than any of this. But we have a bunch of observations that either we collected in the field or come from Wallace. And we have an RSL prediction at that observed location at the age of that sample. This is what you would get typically from a GIA model. Samples have different indicative ranges or indicative meanings, right? A tidal notch, does that mean sea level or near it? And a dune is above sea level. And pretty much everywhere we go, there's some kind of tectonic component we have to consider. There's not really a place that's not moving. That's sort of what goes into our equation. GIA is a function of space and time, this RSL part, and the samples, their tectonic uplift rate gets applied to the age of the sample. And essentially what we do, we build this statistical model. We build a model that says, I'm going to predict the elevation of all your observations. And then we have to sort of score how well that prediction does. And the way we do that, this is just a depiction of what one of the observations looks like in the field. So say I have my GPS and I sit it on a coral, and that coral is 4.1 meters above sea level, and my vertical uncertainty is 0.1. This is the Gaussian distribution. And if my model predicts an elevation for this observation of 3.9, then the likelihood of that prediction matching this observation is 0.54. Better predictions, they score better. And essentially, we use this very simple framework to throw away things that don't fit and keep things that fit. The complicated part here is how do we deal with this RSL? And when I said we started building some of the tools in that 2021 paper, what we were really doing was coming up with ways to consider a wide range of types of indicative ranges for our samples, indicative meanings. I don't know why I wrote range here. Sampling a bunch of different kinds of ages, so things that aren't just constrained like a coral age, but superposition ages, things we might just say this could be anywhere during 5E. How do we incorporate that into this framework? So those tools sort of existed, and a lot of what we've been working on the last few years is how to sort of improve this GIA side so that we can expand it globally and actually back out the ice histories. And the total eustatic peak is still an interesting number, so I'll show you that too. For the GIA, essentially what we have right now is a set of 3,600 distinct GIA models. We vary the rheology of those models. So we have different lithosphere thicknesses and different mantle viscosities and over 100 different ice histories. So we have 5 different independent ice sheets or ice evolutions that sort of get scaled in time. So you could imagine a full collapse scenario of WACE. There's one geometry on how that happens. But in some of the GIA models, we only get it 10% of the way there. In some of them, we get it 30% of the way there. And when it gets there happens at different times. So we're sort of scaling how the Laurentide and the Greenland ice sheet and the Antarctic ice sheets evolved during the last interglacial. So built into that is that fingerprint component that would show up in our predictions of GIA. And to sort of apply that in an inference framework, essentially we want to be able to make these sort of GIA predictions hundreds of thousands of times for all of our samples. It's something we have to calculate a lot. So we had to come up with a way to do this very quickly. And we didn't want to be limited to just this range of viscosity and lithosphere thickness, or even this range of ice histories. So we used neural nets to sort of bridge the gap here. I call these things emulators, but they're pretty dumb. Basically, we take our data locations, and we take that set of 3,600 GIA models, and we pull out all the input information, so the parameters that went into the GIA models, the lithosphere thickness, the location of the samples, the ages of the samples. And then we go to the GIA model and we look at what is the RSL at that location for those parameters. And then we train a neural net to sort of take us from this left side, these different inputs, to the RSL predictions at all of our locations. 10 of the parameters are used to describe the ice histories. I'll show you that in a minute. And then the rest are either dealing with the sample, time, or the rheology. This is just a cartoon of what that neural network looks like. There's actually sort of 128 of these neurons in sort of 5 layers. But this is really like an F1 car. It's not meant to be sophisticated. It's meant to be fast and simple, because we have to do the forward pass. Once this is trained, we sort of recode it into our inference model, and we do the forward passes there very, very quickly. Some examples of the emulator sort of hitting those targets. The blue line is what comes out of just a forward pass through that network after it's trained. The orange dots are just observation. These are model target values from one GIA model at one location. What's really key and what we really wanted to be able to do is sort of smoothly vary how the mantle rheology and the lithosphere thickness sort of get simulated in our inversions. Try and speed up here a little bit. The last trick that I'll sort of show you here was we had to figure out how to deal with the ice part of this, right? So when we think about making that predictive model, we want to be able to sort of simulate a bunch of different random inputs. And it's easy to do that if the inputs are sort of a Gaussian normal distribution. I can use any kind of number generator, random number generator, to draw a value from this distribution. But the ice histories in the GIA models are these sort of 4D matrices, right? It's a full geometry that's melting at different times and sometimes doesn't melt as far as in other models. So we needed to find a way to sample that space at inference time without sort of trying to make up versions of this geometry on the fly. And so we use a second kind of neural net even before we start setting up the emulator, where I also think it's kind of a silly thing, but we take that complex ice history as an input to this network, and then we pass it through some math. You don't have to worry about what it is. And what comes out on the other side is supposed to be the same thing that went in. And the key here is in the very middle, we compress it down to just a 2-dimensional space and add a little bit of noise. And so once this autoencoder is done training, then those same complex 100 ice sheet histories have sort of been remapped or compressed into this 2-dimensional space that I can sample like that normal distribution. I'm going to skip a few things so we can get to the fun stuff. So that framework, what I just showed you, sits inside of a model to make these predictions for all of the observations that we want to run. And we're sort of at the stage now of deploying this beast onto the Wallace database. So this is 775-ish last interglacial observations from Wallace. So it's not everything that's in Wallace, but Alessio and Ciro and Silas have been helping, and Jackie have been sort of pulling what can we use from Wallace. And I'm going to keep paring this down here in a moment. I'll show you what we're using right now. We want to get to here at some point. There are 608 sea level index points in here and 166 limiting data. And one thing I kind of skipped a minute ago is that the rheology part of the GIA model, we actually simulate it differently in different locations. So the Bahamas can have a different viscosity structure than Western Australia. But both of those predictive models have to share the same ice configurations. So essentially, we have a bunch of different regions that can have their own rheology that gets constrained by local gradients and sea level, but they all share the same ice history. So we have 16 different regions, and right now, only 8 of those are we actually running the inference on. And the big difference between this page and this page is these are the locations where we've been able to put some kind of constraint on the tectonic uplift or subsidence rate. So I don't want to show you results here yet because there's a lot of things we know we need to at least put a number on or some uncertainty, and we haven't done that yet. But I'm going to show you an inversion now on all of this data. And the first thing we're going to do is actually go back to those observations from Long Key. This is now a timeline from the start of the last interglacial on the left to the end on the right, and elevation on the y-axis. And the 2 dashed lines, these are sort of the min and the max RSL values for this location in the Bahamas. So the most extreme version of all of those variations on ice history and rheology can get us to about 10 meters of local sea level. And at the bottom, we're pretty much around 0 here. The 2 observations we had, this is that coral at 119. It's about 4 meters high. And then above it, I'm actually showing the berm, so the surface that was above those fenestra. So this is superimposed above here and has, by itself, we wouldn't really know anything about the age of this other than that maybe it's MIS5E. And when we get done with the inversion, and this is run on all the data I showed you, we're just looking at this one location, we can see that this coral was growing in maybe a few meters of water depth, and sea level was mean sea level was sort of coming in just below this berm. And this curve, this is the local sea level curve that comes out of our inversion. We can pop over to the Seychelles. I knew Andrea would show some of the Seychelles data. This is not the new data. This is the old data, but it'll still be fun to look at. And we can see how that same calculation that fit all of the data in the Bahamas, we're constraining the ice history with all of these regions. Let's see what it says for the Seychelles. So we have 7 corals that sort of pass through our most strict screening criteria here in this data set. And we can see that sea level can be much higher here than Long Key, right? So the prior is a little bit wider. And this is the RSL posterior curve for the Seychelles. And just from looking at Andrea's data earlier, I think what's going to happen when we get the new data in is this peak really needs to move a little bit more over here. So it'll be interesting to see if that's what happens. Okay, so let's look at what that data and all the other data actually says about the ice sheets. So right now I'm showing sort of the full range of ice melt scenarios that are sort of considered in that 100 model set. So in the upper left, we can just look at this Greenland ice sheet plot. Gray is sort of, we have versions of the Greenland ice sheet that barely melt beyond today's extent, and we have versions that melt well beyond. And the bottom right here, this is that total eustatic sea level value. And we have combinations of these ice sheets that leave us somewhere around 0. So the LIG looks like today, all the way up to about 15 meters. Now in color are the posterior inferences from that small data set, that preliminary data set I showed you. And there's a few things that stand out to me. We can jump to sort of the numbers to compare to Bob Kopp's 6 to 9. We have something like 3 to 8, not that different. Noticeably quite different than the Bahamas run on its own. A lot of that same data is in here, so we're trying to look at what that means. But I think some of the things that really stand out to me, one, this Laurentide ice sheet that melts earlier, right? So we have some scenarios where it could have melted much later. The data doesn't like that, but if you look or you squint, it's okay with a little bit of persistence, a la Roger Creel's recent paper, a little bit of persistence into the interglacial. And there are some maybe oscillations associated with that in some of the local curves. Data from Majorca really forced the posterior to have a small Eurasian ice sheet. And the way we simulate these two is they must sort of covary or anti-covary. So there's something going on here that also helps sort of from Majorca force the Laurentide big. If we look to Antarctica, it's hard to know if the model right now is learning very much from this data. So on the right side, you can see the colored part almost matches the gray, right? So the posterior is sort of wide open. Maybe more data is going to help with that. I know that there's some data here in Majorca that is really hard to fit without getting a lot of excess melt early. So this version of the inversion didn't seem to pick that up, but we have some other simulations that do. So this is quite preliminary, but it's a bit beyond a proof of concept at this point. I mean, we're kind of confident that the data we've put in at this point is really good. So to conclude here, I'll just give you some idea of where we're going next immediately, and then I have one slide at the end on where we're going slightly longer term. We really want to finish sort of getting more of the Wallace data into this framework. We need to keep working on getting better estimates for uplift and subsidence rates. We're working on exploring the sensitivities of the inversion to different subsets of the data. This framework we've built is fast enough now that we can actually do a lot of tests and sort of explore and analyze these results a lot and think about them. So that's really fun. This idea of different 1D regional models being applied in different places but sharing an ice history, I kind of call this a Frankenstein. So we have some ideas on how to use 3D GI runs where we sort of know the ice history to try and test if that's reasonable, is that causing problems? And of course, if anyone here has feedback about certain data or things we're doing, we'd love to incorporate that. Skip this one. I'll just finish here. The talk had a subtitle that was From Warm Coast to HISEAS. So HISEAS is a recently funded project with the 5 sort of PIs here at the top. Some that you'll recognize from this community and the PALC community. And the goal here, well, part of the goal in that proposal was to build this framework you just saw. So we're doing good on that. But there's a lot of other sort of Earth system and climate modeling that we want to start incorporating and iterating on with results from models like this. And so we're really just sort of spinning up at this point. I think a few grad students have been hired. We don't know if year 2 of the money is coming in. But I'd say if you have students or you're looking for grad student opportunities, then these 5 PIs here at the top, you should reach out to them because we're thinking about problems like this fingerprinting of melt. And I'll end there.
Perfect. Thank you.